Hi, I'm Lane from Cisco. In this video, I want to talk about one of the less commonly discussed aspects of power and power efficiency in routers, and especially in large SP routers. Normally, we just talk about how much power the router is consuming, and we don't spend enough time talking about how much power is actually being pulled from the facility. And we'll talk about the differences there in a moment. I'm going to focus on examples from the 8000 series when I talk about power allocation, but these issues really apply to all different types of routers and switches. They're probably most relevant to systems with more than a few power supplies because they often have complex allocation schemes that determine how many power supplies you want to put in. So we'll talk about power supply efficiency and what drives it, as well as power allocation, which therefore drives the number of power supplies that are needed. We know that you have different ways that power impacts your business. Obviously, every device needs to have a power, and there's a cost to that power. For some businesses, we know that it's really about power consumption. So that's where your model might just be like at your house, where you have kilowatt hours. In other places, maybe it's like a co-location facility, you're paying for each power feed, and it doesn't really matter how much you consume. There are also times when it's a combination of both. Let's say you own the facility, you're paying for the power feeds and you're paying for the power distribution equipment, and then you're also paying for what you're going to consume. So there's different ways to look at it. Some people even maybe looking at carbon offsets for their emissions. So we know it's very complicated, and we're trying at Cisco to address all aspects of your power and sustainability goals. One of those aspects is power supply efficiency, and we'll talk about that in an upcoming slide. In the past, we sort of waved our hands and said about 92% when you get into the Cisco Power Calculator. That's the ratio of or the amount of power that the system is consuming versus what the power supply is taking out of the wall. So the power supply sort of consumes some power to its voltage conversion, and that is something that we can optimize. And one of the ways we can optimize it is by having the right number of power supplies. And by doing better software power allocation, we can help influence that within the router. So at the end, I want to talk about some innovations we've done on the 8000 series. So one of the first things to think about is, what are we actually optimizing for? The terms I'm going to use in this talk are system power and facility power to talk about two different things. System power is the power that the power supplies are providing to the components inside the system. Facility power, or sometimes wall power, is the power that the power supplies are taking out of the facility. If you're paying based on your power consumption, what you really care about is your facility power. What you should care about is your facility power. And that means that you should care about the efficiency of the power supply so that we're not giving up a lot of power just in that voltage conversion or rectification or AC/DC that's happening in the PSUs. So that's step one. The next thing is, long-term power consumption. If you're looking at consumption, you have to recognize that, what is the normal temperature of your facility? That probably impacts how the fan's going to operate. You also want to understand, are your routers having the same type of load all throughout the day, or is there a busy time and a quiet time? Because if your router has a variation, how much power it takes with different traffic loads, and some do and some may not, the ones I work with certainly do, you want to understand what that average load is over a period of time. The next step is power provisioning. And the idea with power provisioning is many of you pay in whole or in part based on how many power connections did you put into the system. So with my products, it's often 60 amp, 48 volt DC or 220 volt 20 or 30 amp AC. And so you might be paying maybe $10,000 per year for one of those power feeds, and minimizing the number of those power feeds is your goal rather than exactly the actual wattage or the average draw. So we'll talk about how you can do that. And a lot of that's around provision power. The idea of provision power is that in order to boot something that's being put into the router or a modular system, you need to make sure that you have enough power for that to function correctly, and therefore you're going to take some power from the global pool that's available and you're going to provision it. Okay. You also may have something else. What other factors do you look at with power consumption? Feel free to put those in the comments and we can have a discussion. So I think there was actually some discussions recently on some of the standards bodies about this, about how does power vary, and there's no one right answer to this. Typical power might mean for you that you're going to send IPv6 1200 byte packets at 50% during the peak of the day and 5% in the evening. For someone else, it might mean they're sending mostly 9,000 byte packets to maybe copy a movie back home to the studio. Lots of things that you could do. Different devices may not vary with the traffic load or with temperature, but others do as well. That can vary based on the silicon process node. So it might be that, for example, 7 nanometer is more dynamic than 28 nanometer. It can also vary based on the architecture of the chip. Some devices are better at saving power when they're not as busy. This can be clock gating and other things, or even running different parts of the chip at different speeds. Also, with Silicon One, we talk about a run to completion architecture, which it means if we need to do some extra work to forward a packet, we don't always have to do a double operation of recycling the packet. That's something else that can save power. Within a specific ASIC device, I like to think of it as some combination of core power, analog power, and dynamic power. And so the core power is, imagine you need to turn off all of the interfaces on this device. You still need some amount of power to get that chip up and running. The analog power is when you're turning on all of the I/O that's connecting to the fabric or connecting to the optics or connecting to anything on your device. There's a certain amount of power that takes. That also tends to be somewhat static in that it's either on or off, and that's characteristic of analog components. Then there's also often dynamic power, which on my devices, what we see is that when we start putting packets per second or bits per second through the devices, they will take extra power. Depending on which system you're working on, it may be that those are sort of sort of 1/3 goes to each if you're at max load, or it may be mostly analog or mostly core. It all depends based on the system that you're running in. Power can also vary on how you're using the device. If you have a device that you're using just as a fabric chip, it's going to have less dynamic components because the lookups for fabric aren't as complicated. If it's a standalone device with lots of I/O, connecting to the network, it may have more power on that side. So things can vary. One of the important factors in modern high performance routers is the power of the optics. If we went back 10 or 15 years, the optics were kind of a rounding error relative to the core chassis and the ASICs. Now I have systems that I work on where the optics may take twice as much power as the rest of the system. And the reason for that is we've been jamming more and more and more functionality into these very small optics modules. So we first had standalone transport equipment, then we started bringing larger DCO optics into the routers, and now we have very small optics in QSFP PDD form factor that can drive thousands of kilometers on a single module. to do that, we have to put a lot of power into that module, and we actually put a lot of load onto the host router to cool that. Well, what I do see for the most part is that optics power is relatively independent of traffic. Once you're dealing in analog, you're really talking about like high and low signals, not zeros and ones. So there's no chance to rest if there's lots of zeros, for example. Now, there are some exceptions to this. With the coherent optics, the more traffic and the more noise that's happening on the signal, you might have to do more decoding to clean it up. So there are some dynamic components there, but for the most part, when we model things, we think about optics as having a relatively constant power, compared to any kind of traffic load. So that's thing one there. The next thing is voltage conversion loss, and this is something that we maybe don't discuss as much, and it's kind of behind the scenes, but I do want to explain that there. So let's say I have let's call it a one rack unit system, and I've got my ASIC here. I've got a bunch of optics, well, just 4 optics here. I've got power coming into the system. It's going to the ASIC. It's going to the optics, etc. Now, the system itself is probably going to have 12 volts or 54 volts or something like that being distributed around to the components. The ASIC will need that converted into some 1 volt or something like that for its operation. The optics need it converted, I think it's 3.3 volts. So to do that conversion, there's a device called a point of load, or POL. That POL is going to have its own efficiency. So remember, anytime we convert voltage, we're going to have some power loss. And what this means is that if I put a 10 watt optic into a router, I might be taking 10.8 or 11 watts of power from the system, and then therefore maybe even 12 watts of power from the wall, because we have that efficiency as well. So just to be aware, there is a voltage conversion loss. Usually it's hidden inside the system, but as I mentioned, we've got times when the optics are now taking 2/3 of the power. If we're talking about a unavoidable, 8 to 10% loss in the voltage conversion, it does end up being significant. So it's good to have some awareness there. Finally, there's a lot of variation among optics modules. In 400 gig, you might have a DAC cable which takes no power, a active Ethernet cable or active electrical cable which takes 4 or 5 watts, a gray optic which takes 10 to 12 watts, or a ZR plus optic or bright ZR plus optic which takes 25, 26 watts. So there's a very wide range of power that these devices take today. Another thing to be aware of, and this is going to kind of come back into power provisioning and why there is an unavoidable gap between the typical power and the amount of power we have to provision, is fan power. So what does the fan do, right? The fan pushes or usually pulls air through the chassis. Usually we have what we call port side intake, which is the fans are in the back and they're pulling air in from the front. There are some special applications where we go in the other direction. But what the fan's doing is it is spinning and it's moving air. We need that air to flow over heat sinks for ASICs, optics, CPUs, maybe even flash disks, different devices in the system. We need to move air along. There's 3 main acronyms that we talk about when we talk about the fans. And so the first one is PWM, or pulse width modulation. PWM is the request that we're giving the fan for how fast it runs. So the software may say it is 30 degrees in this room, therefore I want the fan to run at 52 or 58% performance. And so PWM is the way that the fan gets programmed from the CPU that's controlling it. RPM is how fast it actually runs. The RPM, if I configure 58%, it should be approximately 58% of the max RPM. But these are analog devices. There's friction, there's temperature of lubricant, there's all sorts of things going on. And as fans fail, they may not meet all of the requests of the PWM. So RPM is how fast something's actually running. And then CFM, the way we measure the amount of air moved is in cubic feet per minute. That's a worldwide metric. It's just the one we've got. So CFM is how much air is moving through the system. You can set fan speeds in different ways. It might be just based on the devices you put in the system. It might be based on the ambient temperature. It might be a combination of that. But here's where it gets interesting. The fan power is cubic. And so what that means is, let's say I have a line here, which is my PWM. So let's in this case say that the RPM and PWM kind of map well to each other. The challenge is that the actual fan power does something like this. It's called the fan affinity laws. So what happens is, important to notice is the difference between maybe 20 and 30% is only this much difference in fan power. But the difference between the difference between here and here, this may be difference between 90 and 100%, but the difference in fan power is much greater. Okay, so these things are cubic, and so therefore it's really important that we try to keep the fan power down, especially from going maybe above 70% in typical operation. At the same time, the products that I work with are rated to go up to 40C operation, and so even if you're normally operating at 25, 26C, I have to be ready for that fan to go, all the way up here. Therefore, I have to build enough power supplies into the system for that to be possible. And so that's going to be an inevitable gap that you can't avoid between your typical operation and your worst case operation that you're provisioning power supplies for. Okay. So one important thing is, in kind of shifting into power supply efficiency, is to understand the 80+ standard. So the 80+ standard rates the efficiencies of power supplies at different loads. And so we're currently, I think, usually in the platinum and titanium with most of my products. Some consumer appliances, or maybe some older routers, you may see silver and gold. But what this is, the first thing this is showing here is that the efficiency of the power supply varies based on the load. Most systems are often optimized for about 50%. And so the efficiency of power supply, let me see if I have room here. The efficiency of power supply might be somewhat low if it has no load on it, and then it sort of peaks, and then it may tail off a little bit. Now, the standard is a little bit, doesn't necessarily reflect that, but if you can be in kind of this range, you're usually pretty good. But if you've put in so many power supplies that they're only operating at 60%, you may find that you have 80% efficiency of the power supply. So you want to be careful that you don't put in so many power supplies that you're shifting your utilization outside of the decent zone here. So what are the actual requirements? So to qualify for platinum, if you're putting 20% load on your power supplies, so so each when load's shared among all the power supplies, they're only at 20%, then you're going to be at 90% efficiency. So if you pull X number of watts inside your system, you're going to be pulling about 10% more outside the system. Similarly with platinum, if we're at 92% efficiency, if we're at 50% load, we're at 92% efficiency, and if we're at 100% load, we're at 98. So here you see with this system that it is most efficient in these three options in the middle. Although here you see with titanium, it's actually more efficient at 100. So they've done something a little bit different with the requirement there, or maybe the place I pulled this one has a typo. But anyway, usually it's 50% that things are optimized for. On the systems I work with, we often can get up to 96.5%. So the power supplies are quite efficient these days. Each power supply will vary. So like on my platform, the 48 volt DC supply and the 220 volt AC supply will have different curves. There are also some more subtle variations based on the ambient temperature and the exact voltage you're using. But the main idea here is that you want to be kind of in the 30 to 100% range of your power supplies. If they're pulling less than 30% load, you may start to see some inefficiency that you should try to optimize. So we talked about one of the provisioning challenges already, which was the requirement for the fans to be able to go 200%. But what are some other ones? If you look at a typical service provider router, typical router anywhere really, enterprise, maybe data centers are different. What it's often doing is it's going to be busy most during the day. It's going to have some capacity ready if their other network devices fail. It's going to have some capacity available for growth. So we're not even really running at 50%. We often might be running in 5 or 10 or 20% because we're ready. If you look at the 24-hour usage, we're ready for a spike in traffic load due to some failures. We're ready for the spike in traffic load maybe earlier or later in the day, etc. So loads can vary. They usually don't go to what the max is going to be that we could create in a lab. In addition, in service provider networks, we often see that packet sizes are 800 to 1200 bytes, and so that ends up being a lot easier on the router because it's got to do work for every packet it looks up. It's got to access some memory, so that work on the router takes power. The challenge here is that when I want to make sure that my box never runs out of power, I have to provision my devices to be able to handle the smallest possible packets at 100%. If you didn't do that, you would run the risk of running out of power in an extreme condition. And so the difference between that typical power and that worst case power, both for the ASICs as well as the fan, is why we get a gap between typical and provision. Now remember, I said that the optics tend to not have a big gap between typical and provision. Okay. In addition to that, a lot of times, we have these large routers that we don't populate day one. So maybe I have put in a 12-slot router and I'm going to grow into that over a period of 5 or 6 years. Traditionally, a lot of routers would not kind of think about it that way. You would put in a switch fabric card, and that switch fabric card's provisioning would say, oh, all my cards are here. So there's just one value that's provisioned for that. We'll talk about how that's done differently in 8000 series. In addition, in the past, you don't have to go back too far, all the optics were sort of the same power. If you look at the QSFP28 optics, for example, most of them had 3 to 4 watts. Now, there's much greater range, from 0 to 25 watts with the optics we have at 400 gig. The way that we used to do things at Cisco, or we do on all our other platforms today, is we just assume that you're going to have a certain type of optic, usually a worst case optic on all the ports. And so back with the NCS 5500 that I worked on, we would just assume that you had an LR4 optics on all the ports, and we would bundle that into the line card power, and we wouldn't treat the optics separately. We'll talk about how we do that different on the 8000 in a second. So let's now look deeper into provisioning and how that actually shows up on the router. So this is an 8800 router. So this is the modular system that comes with 4, 8, 12, and 18 line cards. This one is from, I think, an 8804. And so the first part of showing power, this is showing that I have 2 power modules. Each of these power modules, and you can just see by the part number, are capable of providing 6.3 kilowatts. This power supply, I know, can provide half that power if one of the feeds fails. So there's two feeds going into it. We have another power supply that's the 30 amp version that actually can provide 4.8 kilowatt if a feed fails. So here we see at this time, this is the real power voltage, real amps on the input and the output side. And based on that ratio, you can kind of see that what the efficiency was going to be. On the 8000 series routers, we can see the power consumption in two different places. One is reported by the power supplies themselves. You can also put an external monitor on, or an external power meter, to double check that you're getting the right value here. From what I've seen, they've always been quite accurate. Remember, and then also you can see the power allocation and the current power for each actual different device, or the main devices inside the system. So when we talked about power supply efficiency, where that shows up is right here. So the PSU efficiency for this router is 4329 divided by 4623. So whatever that is my power supply efficiency right now. I didn't try to optimize the system, so I don't know exactly what that is, but hopefully it's okay. The second part of showing V power for our larger chassis is showing the different power usage and different power allocation for components. And so this is when we get some visibility into the gap between the the current power consumption and the worst case power consumption. And I don't remember off the top of my head if I was forwarding a lot of traffic at the time here. So this might be no traffic, it might be a high traffic load, it might be typical. Sorry, I don't remember. But if we start looking at this system, we have two route processors. They are currently taking 77 and 78 watts. They might need up to 105 watts. So if I take those 6.3 kilowatt times 2 power supplies for the system, if I don't configure it for redundancy, I've got 12.6 kilowatts available to budget. When I want to power these two RPs on, I take a total of 210 watts from that budget. The rest is left over for the other devices. So what are the other devices here? This is our 32 by 400 plus 14 by 400 card. This device needs 796 watts to boot, meaning that if the power table in the system only had 500 watts left and you put this card in, it's going to not fully boot it. It's going to have a little bit of power pre-allocated. It's going to bring up the CPU. It's going to say, hey, do we have enough power for this? If not, it's not going to boot. Now, this is the amount of power it currently has, but it only is currently using 482 watts. If more traffic was sent, it might go closer to that 796. And so here you see for all the other line cards, you see what their power allocation is, and you see their current power consumption. Now, some of these are 36 by 400 cards, and so you see that those are taking more power than the lower bandwidth cards. Similarly, we have a switch fabric in this system. So this is actually 7 of these fabric cards are operational. This one, in the last one is shut down. You see that we have still some power allocated to it. So if it comes in, we can boot it and check if we have enough power. But you can see here the power allocation for those as well. And then remember what I said about the typical power and the max power for the fans being dramatically different? Well, you can see that here. This 8804 is only using about 90 watts of fan power in this typical operation, but it might need 4 times 330 if it went into the max stress conditions with high temperatures and other factors that might require the fans to go up to 100% PWM. Okay, so this is an unavoidable part of the power allocation. I have said that a few times, but that's one of the reasons that the typical and the max are quite different. So now let's shift gears as we wrap up and talk about some of the things that the 8000 series has done to narrow this gap and therefore reduce the number of power supplies that you need. Okay, because if you have a specific configuration for a system, we can put it into the tools and it's going to say you need 4 power supplies or 5 power supplies with N+1 redundancy, or 8 power supplies with power feed redundancy. So by optimizing allocations, we can reduce the number of power supplies you have, reducing cost for many of you. In addition, by reducing the number of power supplies, we're often going to bring the PSU efficiency closer to that middle mark, which has more efficiency in it. Okay, so the first thing is we defer. Remember I said that in the past all the optics sort of had the same power, and so we just bundled that into the cards. Well, that's not optimal if you're not using ZR optics everywhere, or you have some ports that you're not using. So rather than having 32 by or 36 by 25 watt optics included in the line card, instead what we do with the 8000 series is we actually wait until you put the module in. So we pre-allocate 1 or 2 watts for each port, so we have enough power to start booting an optic. But then when you put a ZR optic in, the ZR optic is going to have something in the ROM that says, hey, I need 18 watts. And the router line card is going to say, okay, I've got 18 watts, I'm going to boot you up. What this does is it lets the amount of power for the optics kind of conform to what the optics actually need versus making assumptions on the worst case. And so this saves a significant amount of power for power allocation. Similarly, we have some line cards that have support for MACsec, and these devices require MACsec to be turned on. It's not there by default. MACsec takes extra power. It's doing encryption. And so that extra power to do MACsec is not included in the default allocation. But if you go and turn on the MACsec, we may put in an extra 1 or 2 or 3 watts for that. So that's something else that's been kind of deferred. The last part of the innovation is what I mentioned about the fact that we don't always fully populate a chassis. We might have a 12-slot chassis that only has 4 line cards in it right now, and the system is going to automatically shut off all those connections between those empty line card slots and the switch fabric. And because that power can be saved, I don't have to allocate as much power for that fabric card. And so the amount of power allocated for a fabric card is going to vary based on the number and type of line cards that are present, and that can be some pretty significant savings. In addition, we have some customers that run their line cards without all the fabric cards. We actually have N+1 redundancy on our switch fabrics on the 8800. I don't think any other systems on the market have that. If you didn't need that N+1 redundancy, you could shut down one of those fabric cards. You're going to therefore save power because the fabric is down, as well as you're going to shut down the line card links to that fabric card. So each of those may save on the order of 15 or 16 watts for every fabric card that's missing. If you're not using all the bandwidth on your cards, you also may want to shut down 2 or 3 fabric cards. So there's ways that you can optimize the system to reduce the power consumption. In addition, we reflect that in how we do power allocation so that we can reduce the number of power supplies. Okay. So there's a lot more going on behind the scenes there, but I just wanted to kind of, in today's video, talk about power supply efficiency is important, and power allocation dictates how many power supplies you need. Therefore, it's somewhere we want to optimize. Okay, thanks for your time. Please leave a comment if you have any questions, and I'll make sure I address them. Thanks.